Hey guys, welcome to another Estate Treasure video. This time we're going to be looking at a Wavetek Model 132 VCG noise generator. I believe it's from the late 70s. Probably made it for a few years, probably 70s into 80s, I would think. Now I'm doing this for two reasons. One, I want to gradually work through all the equipment I got from the Mr. Lill estate, and two, we are actually going to use this as part of one of the upcoming predictor restorations. Now, I've heard some detractors of Wavetek over the years. No, it's not quite up to Hewlett-Packard quality or Tektronix or other high-end laboratory-grade equipment. But it's not hobbyist grade either. It's kind of in the middle. And what I personally really like about Wavetek is that, at least the equipment I have from them, it's all off-the-shelf parts, readily available. And it's kind of from the era when I was learning about electronics, the 80s into the 90s, where it's all the parts are very recognizable, like a 741 op amp, or 2N3904 NPN transistor, that kind of stuff. Usually they're socketed. It's all very recognizable, very available parts, but it's also very useful equipment. So this one in particular, it's my understanding from what I've read, I've never actually used one of these, but it's my understanding it's an audio generator and above audio. I believe it goes from about 10 hertz to 1 or 2 megahertz, and a function generator. It can do sine, triangle, square wave, but also noise. And it looks like there's an FM mode, so we have SN, NS, and FM mode, and then there's function, which I believe function is just your standard sine, square, triangle generator. You could use the audio range for, say, testing an amplifier or a speaker, which is what we are going to be doing. But it can also generate noise. And I took a peek at the schematic and the service info, and one of the circuits jogged my memory. It's something I hadn't seen in a long time. That being a pseudo-random digital noise generator using, I believe, a shift register hooked up in a certain way that it produces a very, very long random looking pattern, but it does actually repeat. But it's a useful way to generate what they call digital noise versus analog noise, which is usually created using a selected transistor that's especially noisy, and they bias it in a certain way that the junction kind of breaks down chaotically and makes a hiss sound. But something else cool about this, the VCG, voltage controlled generator. You can put in a control voltage, and that voltage will vary the frequency of the oscillator, like an old school analog sound synthesizer, a basic building block. It doesn't do 1 volt per octave or whatever the industry standard is, but you can get a pretty wide range. I think it does like a 1 to 1000 range. So in other words, you can go from maybe say 100 hertz to 100 kilohertz or something like that by sweeping the control voltage. I think something like minus 10 to plus 10 volts. The exact specifics are not important. The point is you can vary the frequency of this device either with the dial or with an external control voltage. This control here and the sequence length all has to do with that noise. So the sequence length refers to that pseudo-random digital noise generator. And this changes the characteristics of the noise. That's a whole weird thing, where there's pink noise and white noise and blue noise. All very useful if you're in the amplifier business and you want to characterize the amplifier you're working on. SNNSDB, I think this signal to noise ratio, I think the idea is you can generate a pure sine wave and then mix in some noise and then see how it affects your circuit you're working on. We'll check those out just to see what it sounds like, but I really right now just care about the pure mode because we want to test the speaker and I want to see if my repairs to it were successful. But let's not get too far ahead of ourselves. Let's make sure this thing even works. Last control here, output attenuator. That seems... oh, that's weird. So the coarse level is down here on the rotary switch. And I was wondering where the heck is the variable fine level control? That's up here on the function switch. Call me crazy. I would have thought the variable output level knob would be concentric with the coarse output level control. But no, it's up here with the function control. Alright, now one downside to this, if you watched my video on the Nixie tube frequency counter, you saw that I had an issue with the power connector. This uses that same kind, and it's really deep set in there too. This is not your modern, I think it's called IEC power connector you've all seen on computers and whatnot. Oh, these guys. This will not fit in there. It's sort of the precursor, well, it is the precursor to it. I've heard, or I got a lot of comments on guys who have retrofitted older equipment to use this, and that is a fine idea. I think it might be a little bit tricky on this one though because it's so deeply set in there. You need to cut out this panel and yeah, who knows what. So what are we going to do? Well, I did take a little look around online. Some of you warned me that they're hard to find, and yes, they are hard to find and they are expensive. They are out there, but I'm not the only one who's got old equipment that uses them, so supply and demand. So what we're going to do is we're just going to cobble something together. So I took a couple Molex pins that are about the right diameter, and instead of feeding a wire into it and crimping it, we're going to use it backwards. And we're going to leave it hollow, and we're going to slide it over the... well, first we're going to attach a line cord. We're just going to blob some solder onto this and take a line cord, just a standard lamb cord. We're not going to bother grounding this. We're just doing some quick tests to make sure it works. I'm going to cut this off, clean it up, tin up two stubby ends, and just tack solder it onto these connectors, and then push these connectors onto that. And that should get this thing operational, assuming it is. And there is Mr. Lil's old label that he put on there to identify it. Before we do any of that, I've noticed these screws. It looks like this is very easy to get open, assuming that's what these are for. Wavetek stuff is very serviceable, yes. I think they're still around. I could be wrong. This is a little bit earlier than the other stuff I've seen. Instructions a little different. Well, that doesn't get us too far. It's loose, but not quite coming out yet. This comes off. Okay, beautiful. There we have it. Beautiful 70s vintage analog electronics. Let's see if we can find a date code. 7508, 7443. I'm thinking this was made early 1975. We have a few integrated circuits, although I think some of these are dual diodes, dual transistors or transistor arrays. Like that guy down in there, I think is actually a dual transistor. There weren't too many op amps yet on the market in the 70s. Boy, there's more stuff down here, but I'm not going to take these boards out. I don't want to mess with it. Wow, actually maybe we do want to see that. Holy cow. Okay, so what am I saying holy cow about? These are all integrated circuits. I think that is a massive shift register made from a whole bunch of discrete small shift registers, or maybe just flip-flops. Looks like we 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, Around about 30 chips, I'm guesstimating, just doing a rough count. Wow. No, the circuits I'm thinking of are newer, where there was just one chip that would do the whole pseudo-random noise generator, not 24 chips. That's crazy. How do we get this out? I think we just take 3 screws out. It's an odd way of mounting a circuit board. There are little right angle pieces of metal riveted to the circuit board and then screwed into the side here. Let's see if we can get this out without breaking anything. And here we can see this is part of the noise filter. See a bunch of mica and film caps on there. Switch them in and out to change the characteristics of the noise. I got a feeling there's going to be more to it than 2 screws. It's a pretty big board. There's got to be a big connector going to it somewheres. Well, it's certainly loose. I think we're going to take that out too. Oh, do I hate it when they use a mix of Phillips and non-Phillips screws. I guess that is all bolted in. Plus a bunch of cables. Flip this around. Not easily. There. Okay. Well, we have a bunch of push-on connectors, nice gold-plated. Look like they would. Yeah. So I was thinking they should probably work on a predictor on those vertical stakes. Boy, that's pretty. They use these all over this device. Alright, so this collage of chips here, what are these? They're 74 107s. That number's not ringing a bell. Is it a dual JK flip-flop? Or is that some type of shift register? I'll have to Google that. Otherwise, we have a bunch of glue logic too. 7400, 7486, 7420, 7410, 7404. Those are inverters and AND gates and whatnot. But the bulk of it, all these are 74 107s. The rest of it, I'm going to So say I think that is the output amp, but no. It's an LM301, which is, for the time, a fairly fast op amp. And boy, they sure have it, the big ground plane around it and so on. This is more complicated than I was expecting. For sure. I thought it was just going to be a basic function generator with just a little tacked on noise circuit, but there's a lot to this. Cool. Well, I'm going to look up what a 74 107 is and put this back together, and let's try to power it up. Before I do that though, these caps are kind of neat looking on the side here. Electro Cube. I've never seen that brand before. I tacked on the AC line cord and I pulled out my Hewlett-Packard 54600B digital oscilloscope. I figured it'd be the quickest and easiest way to see if it's actually doing something. Well, let's turn it on. If I knew where the power switch was. Okay, oh, I see. It's part of the frequency control. Sure, why not? Okay, is it on? Don't know. Auto scale. Now, one thing that does worry me is when I was putting that circuit board back in, I saw that a couple screws were left out. So this may have been opened up in the past. Maybe we just have really low output levels. So let's go to a fairly large output. Sine wave, about 1 kilohertz. And run function, output, level. Well, that's a little disappointing. I'm still not even sure if this thing's turned on. Oh, you know what? It's not. And you know why? I didn't plug it in. Okay then. Oh, we all make mistakes. Let's see. There we go. Now it is plugged in. Usually Wavetek stuff has a kind of a light somewhere to tell you it's on. Let's see. Yes, that is glowing. Well, you can't even see that, can you? No, you can't. There we go. Boy, I'm being very, very unprofessional today. Okay. Now, auto scale. Ooh. Well, at least it's on. Ah, there we go. Ooh. Hey, and it varies. Hey, so that's square, triangle, and ooh, that's a mushy sine wave. Now, this is 50 ohm output impedance. I'm running it into 75 ohm coax into a scope with a 10 meg input impedance. Nothing's terminated and really essentially no load on it. But I figure for frequencies in the kilohertz, it's not going to be that big a deal. So it's probably not what's clipping the sine wave. But the sine wave is definitely being clipped. Well, let's play around with this a little bit more. There is the random. Oh, so that's the random digital mode, I guess. And let's see as we vary. The frequency control does not seem to be doing anything. This should. Maybe. It might just be too darn hard to tell what's doing what. Okay, this definitely has an effect. The noise frequency. Oh, this must be what controls the clock frequency into the pseudo-random digital noise generator. And that is coarse and variable. Nifty. Alright, let's get to the mixed mode and see what that looks like. So, there's SN and there's NS. So, signal noise, noise signal. Does that mean that there's more signal than noise? What is happening? Okay, I'm at a very low frequency, that's what's happening. So there's definitely jitter to it. Let me zoom in a little for you guys. So see how the whole thing's kind of vibrating a little bit. Ah, see, I believe that is the added noise. You can see it up there at the top. And I'm thinking this middle control, yes, the middle control controls the amount of noise that's getting added to the signal. That is pretty darn cool. And let's see, with triangle, sine wave, you get even more obvious what's going on there, or it gets even messier, I should say. It may seem like a strange thing to want to do, because you're always trying to eliminate noise from an amplifier, right? But when you're designing it, when you're testing, you actually want to put noise into the signal in a very controlled way, so you can see how your device reacts to it. That's the SN mode. Now let's try NS. Ah, that's what I thought. So this, I think, is mostly noise with a little bit of signal added into it, whereas before it was signal with a little bit of noise added into it. And the final mode, oh, FM is, it looks like it's an option. In other words, you can use FM with any of these. So let's see. So I'm just in pure function mode now. A nice triangle wave. If I put on FM, it starts wiggling a little bit. It's being frequency modulated. And it's being frequency modulated by a frequency determined, apparently, by what was previously controlling the noise clock. So adjusting the noise frequency is controlling the FM modulation of the triangle wave. Obviously, I haven't read the manual. I figured I'd just figure it out as we went along. You know what? I think it's being randomly frequency modulated, which would introduce jitter into it, I guess. Should be really obvious with the square wave. Alright, so it does appear to be fully operational, with the exception of things being clipped. I noticed the triangle wave is also clipped if I go full amplitude. Actually, that's full amplitude. Now, that could very well be the power supply. There are adjustments for regulated, it's probably plus minus 15 volts, something like that. That may need a little bit of adjustment. The filter caps may be a little tired. And as far as the sine wave goes, so what the typically function generators of this era, the way they work is they use a basic multi-vibrator circuit, which produces a triangle and a square wave very nicely. Getting the sine wave is the tough part. So usually what they do is they take the triangle wave and they run it through a selective wave shaping circuit to make it into a pseudo sine wave. And sometimes there are adjustments for that to adjust the shape of the waveform. That might be what is off, but it also looks like it's being clipped. Well, it's weird because even if I decrease the amplitude, the clipping never changes. In other words, it's not like it's only clipped when it's at maximum amplitude. It's always looking like that. So I think it's the wave shaping network that isn't working quite right. But for our purposes, what I want to do with it right now, that's just fine. So let's get to the next part. It's reassuring to see that I do still have a few functioning brain cells left. Yes, the 74107 is a dual JK flip-flop. Here is the manual for the Model 132 Wavetek. I'll leave a link to it in the description. This is 1981, but as we saw from the date codes, the original device was introduced much earlier. It's a very comprehensive manual with circuit description and theory of operation and whatnot. So there is that pseudo-random sequence generator that makes the noise. I didn't realize they used a digital to analog converter out of that. I thought they just, well, interesting. And so the output of this will be that random kind of crazy square wave we saw. But apparently they take that and convert it to analog and then mix that in with the output of the function generator. And there's that sine converter I was talking about that converts a triangle to a sine. Oh, this is the shortened version. That's it. I know there's a version that has the schematic and parts list. Let's see if I can find that. This looks more promising. The previous manual was 15 pages. This one is 51. And this is 1978. Same circuit description and so on, but now we get the maintenance. So this should have info on probably how to fix the issues that I saw with it being clipped and whatnot. Sine distortion, amplitude and balance. That's that sine wave converter. Alright, let's get to it. There's how the main boards connect together. Parts placement, here we go. Schematic. Wow, and it is a hand-drawn schematic for sure. A rather difficult to read one at that. Oh boy. A few more integrated circuits than I expected. So there's a number of micro A709C, that's a classic old op amp, as is the CA3030. I think that's a differential amplifier maybe. There's a discrete differential amplifier, more 709s, discrete transistors, a lot of matched pairs with these transistors. Now even though these are off-the-shelf parts, I still wouldn't want to try to fix one because some of those matched pairs might be a little tricky to get right. There's the digital board. Where's the schematic for the digital board? There we go. Well, there's a lot of parts to this, but the schematic is actually fairly simple. There's all those JK flip-flops going together. But they don't just connect directly together. They connect up through these various gates, and that's what makes the crazy random pattern. It's a combination of flip-flops. A flip-flop, if you don't know, is something, well, just like it says, you could, depending on how you hook it up, you can have it, the outputs flip-flop back and forth on every clock pulse. But there's also a data in and a clear, although JK flip-flops are a little different. But basically you have two inputs and two outputs, and the two outputs are complementary. And then they're taking the outputs of these and feeding it through, looks like, well, NAND gates, XOR gates, inverters, and it's feeding back into itself, making a very complicated pattern. And that's what makes noise. That's the output attenuator. Alright, so if you really want to read up more on this classic old school design, this is a freely available download. I will link in the description. So what is the next part? What do I want to use this for? To test this speaker. In an upcoming restoration project you're going to see. Well, actually, you already did get a peek at this. This is the speaker from the set that is horribly corroded, and the speaker cone was trashed, had a nut jammed through it. I'm not even close to starting working on that set yet, but I wanted to see if I could salvage a speaker sooner than later to see if I would need to try to source a replacement. So I just quickly cleaned it up and patched it using coffee filters. I'll go into what I did in more detail in that project video, but now I want to see, does it actually work? It seems to, the cone seems to be in pretty good, the repair worked and the voice coil isn't rubbing, but let's see what it actually sounds like. This is going to be, I think, 4 or 8 ohms. This is a 50 ohm output impedance, so it's not exactly cool to just connect this directly to this. In other words, it's going to be really loading down the function generator. So I'm going to add a resistor in series with this 33 ohms, something like that. So I don't expect to get a ton of volume out of the speaker, but we should hear something if it's good. Okay, speaker hooked up to the output of the generator. One side of the voice coil going directly to the generator, the other side going through a 33 ohm resistor to the generator. We are at 1 kilohertz sine wave. I have the output level down really low. Let's start increasing it. Yeah. Sounds odd. Sounds strangely modulated. Oh, because I had the FM turned on. It sounds like it's dying, but there we go. Not regular low frequency response. Well, I mean, good enough for what it is. Seems to crap out around 40 or 50 hertz. Alright, let's try mixing in some noise. I'm not really hearing the noise too much. Oh yeah, okay. Yes, now we hear the noise. Yeah, and this is the mode where it's almost entirely noise. So if you were designing like a noise rejection filter kind of thing, this would be great for testing it, because you can get rid of all that and get a clear tone out of it. You've done a pretty good job, I would think. Alright, well, now we have one last thing to try. Let us try feeding something in to the VCG in and see if we can alter that. It basically would be frequency modulating it with an external signal. It should sound, well, we shall see how it will sound. Alright, so what are we going to modulate the VCG in with? Well, I brought out a related Wavetek product, a little bit newer, the Model 183. If you like playing around with audio analog waveforms, I highly recommend the 183. It's a lot of fun. Not only is it a function generator, like the 132, but it's a sweep function generator, meaning you can set the a range of frequencies and it'll sweep through them, and you can control the rate at which it sweeps through them. That combined with this should really allow us to make some interesting sounds. All we need to do is connect the two. And this also has a VCG in, so you could have this go to yet another device and you could chain a whole bunch of them and have all sorts of fun if that's the kind of thing you like to do. Alright, power. And this also has the glowy frequency indicator. Let's see. Let's go to the audible range here. There we go. It's weird to be getting the sweep, but there's also a fixed tone that's very prominent. Like I said, lots of fun. Alright. Oh, I could spend hours playing around with this stuff. I gotta get back to restoring some predictors. I hope you guys enjoyed this look at a Wavetek Model 132 VCG noise generator from the mid-70s.